So there isn't enough time to get that next.
I genuinely, I never showed any derivation. When I looked at the case textbook, there's actually a derivation that actually cuts side.
Let's see, we went for again, often at the expense of those who just needed to write. They were never going to understand how.
Yeah.
They got less time for that.
All right. Nice meeting with you.
Needed it.
Believe it or not, we are starting the last day of summer school. And it's not the least day. We have 3 lectures covering small X physics, technology, and calorimetry. The first lecture is going to be the second lecture in the series of small X physics by Sievert.
All right, well, good morning, folks. I'm excited to be back for part 2 of our discussion about high energy QCD or small X physics. So maybe let me start with a review of what we talked about yesterday. We spent all the time at the blackboard and we computed 2 sort of elementary processes in QCD. The first one is elastic quark-quark scattering as an illustration of high energy scattering. One can write down the amplitude in general. There's also a U-channel amplitude, but in the limit S much greater than T much greater than lambda QCD squared, only the T-channel amplitude dominates. And then you can further simplify the kinematics so that the amplitude scales like S over T. And this is a really convenient form because the factor of S in the numerator exactly cancels compensating factors of S in the definition of the cross-section. So that when you get the cross-section, say differential d sigma dt, your answer on the right-hand side is independent of S. So it goes like S to the 0 power in the limit S going to infinity. So it's unsuppressed in high energy scattering. This was sort of the tree level baseline. We had d sigma dt, and then we computed radiative corrections to this process. We focused in particular on these diagrams A and B in Feynman gauge. Computing A and B, I can obtain C and D for free. You have to do a separate calculation of the non-abelian gluon vertex for diagram E. The details in particular that we worked out was the sum of the initial state radiation plus the final state radiation. And we saw that there was a remarkable cancellation that happens. Basically, these 2 diagrams have identical kinematics in the high energy limit up to a minus sign. The minus sign is entirely due to the fact that the intermediate propagator is going in a time-like direction in one, space-like direction in the other. And that minus sign leads to an almost perfect cancellation of the amplitudes, except for the fact that in QCD you have color matrices. And so that instead of getting 0 when you subtract the amplitudes that are kinematically identical, you get a commutator. And the commutator produces the structure constants FABC. And it's no accident that that form is exactly the same form as the trigluon vertex. So because of this, when I add up all the diagrams on the right, it has the form of the trigluon vertex overall with a different momentum dependence. This is known as the Lipatov vertex. And if I take this and square it and compute the cross-section, then this triple differential cross-section was what I get. Again, completely independent of the center of mass energy S, also independent of the rapidity y of the produced gluon. And then when we use this as a way of defining a gluon multiplicity, the cross-section normalized by the tree-level elastic scattering, then we again get a gluon number distribution in the final state, which is boost invariant. And then if I trivially integrate that, I get a number per unit rapidity, which is approximately a constant. That's even what you see experimentally, that the number distribution of hadrons in high energy scattering around mid-rapidity is basically flat. And this theoretical approximation suggests that it should be approximately flat until you start to get close to the actual beam rapidities, which are something like plus minus 5 units in rapidity. When I take that rapidity-independent gluon distribution and I integrate it over the rapidity, I get a factor of the total rapidity of the collision. And the total rapidity depends on the center of mass energy as a logarithm. This is what leads to an enhancement in the number of gluons produced in the final state due to the large phase space that competes with the perturbation theory coupling constant. So we're normally working in a limit where alpha S is small, but the log can be large. And potentially, if the log is large enough that it starts to offset the alpha S in the power counting, then I completely change the nature of my perturbation. I'm not doing dilute QCD expanded around the vacuum anymore. I'm solving a problem where one gluon emission is of the same order as 0 gluon emissions, and 2 gluon emissions is of the same order as 1, and n number of gluon emissions is always of the same order. So you have to consider not one gluon emission, but arbitrarily many gluons that are radiated in the final state around mid-rapidity. So today I want to take that background and connect it to deep inelastic scattering and definitions of X. I want to show you how that building block shows up in our PDFs and how that leads to gluon saturation and why it's so important that we find it or rule it out. So a few basics. These next slides are sort of general comments that I give introducing deep inelastic scattering. So this is probably at a very low level for you. When I introduce the idea of deep inelastic scattering measuring the structure of the proton, I always put it side by side with the atom, because we know that both are composite particles. They're not fundamental to each other. They have internal structure. And that internal structure is a reflection of the force that binds them together. So in the same way that the structure of the atom, all of its electronic orbitals, all of electronic chemistry is a manifestation of quantum electrodynamics. The orbital structure of quarks and gluons inside the proton, the nuclear chemistry of how they interact with each other, that's a reflection of QCD. So we study proton structure in order to better understand QCD in the same way that we do precision atomic physics to better understand electromagnetism. Both the proton and the atom were discovered simultaneously about 100 years ago, and it's no accident. Of course, famously, the way the nucleus was discovered was by Rutherford's gold foil scattering experiment, where he essentially created a very rudimentary form of an early particle accelerator using a radioactive alpha source. And while most of the alpha particles had small angle deflection, forward scattering, every once in a while you would see a hard scattering event, large Q squared, that would deflect the alpha in the opposite direction. And that large Q squared hard scattering was the evidence that there was something local of size 1 over Q in the atom that contained that positive charge. So 100 years ago, we came up with our understanding of the structure of the atom and the existence of the proton. Since then, our understanding of QED and atomic structure has grown astronomically. It's insane to me that we can compute theoretical quantities up to an insane level of precision, like 1,100 digits of precision, 891 for-loop Feynman diagrams. That just blows my mind. We not only have the theory so well under control, the experiment is so well under control that measurements of the hyperfine splitting of cesium-133 are the most precise definition available to us for the second. So we understand atomic physics so precisely that we literally use it as the definition of time. In contrast, we know all of this stuff about the atom. The atom is all grown up. Meanwhile, the proton is still a moody teenager telling us, you will never understand me. In contrast to everything that we know at great precision about the proton, we don't even know where macroscopic quantum numbers of the proton come from. How does the proton spin arise from its quarks and gluons? How does the proton mass arise from its quarks and gluons? Which radius is the correct radius for the proton? The reason that these are so complicated is because QCD is so complicated. It's much more complicated than QED. Why? QED, as everybody knows, is a linear theory of charges and fields. It's Maxwell's equations. And in Maxwell's equations, we have a beautiful superposition principle. So every undergraduate knows that if I take 2 lamps and I shine lights on the same point, the light doesn't bounce off each other. That'd be crazy. Instead, the light adds together at the amplitude level. Electric field of one, electric field of the other, electric field of the resultant, and then you square it to get the intensity. That's ordinary E&M, and it's a reflection of the fact that in electromagnetism, there's only one type of electric charge. So I tend to say charge is a scalar in QED. It could be positive, it could be negative, but there's no directionality associated. That's what changes when you go to QCD. SU3 gauge theory is very, very similar to U1 gauge theory. You get equations that look a lot like Maxwell's equations, but there's one critical difference in that you've changed the gauge group. You've changed what charge means. And unlike an abelian theory U1, where there's only one type of charge, and if I start with a negatively charged electron and I interact, it's still a negatively charged electron. And if I interact 5 million times, it's still a negatively charged electron. In QCD, you have color charges, and those color charges interact by a rotation matrix. So the way I describe it is to say that in QCD, color is a vector. It lives in a three-dimensional color space. And when I start with a quark in some color direction, the interaction rotates it to a different color direction. And that changes everything. Because now if I start off with a quark that's blue colored, and I have an interaction that turns it red colored, the radiation that I gave off is charged. It has blue minus red net number of color. And that means that unlike QED, where photons are electrically neutral, in QCD, gluons are charged. And that means at tree level, if I shine two lamps of gluons on each other, they will bounce off and interact directly in exactly the way that QED doesn't. So the point that I try to make to an introductory audience is that the structure of QCD is almost identical to the structure of QED that we understand very, very well. There's one change that changes everything. And that leads to the confining potential, asymptotic freedom, the whole 9 yards. The consequence of all of this is that if we want to try to study proton structure, it's much harder than trying to study atomic structure. If I want to study atomic structure, the easy way to do it is ionize an electron out. So you can do something like angular result photoemission spectroscopy in condensed matter physics, where I send in a photon with some known kinematics, I measure the electron that came out, and I directly image the density of states of my The problem is that if you try to do that with the proton, you can't just ionize out a quark and measure the quark. If you try to rip a quark out of the proton, it explodes into a shower of hadronic fragments. Due to the strength of the confining potential, if you take a meson and you try to pull a quark out of it, you don't get a free quark like you would for a free electron. You get new bound states of mesons. This is completely analogous in my mind to the fact that there's no magnetic monopoles. I can't take a magnet and cut it in half and get an isolated monopole. In the same way, I can't take a meson and cut it in half and get an isolated quark. Both are sort of even ill-defined at the level of the theory. Fundamentally, what this means is that particle collisions that are mediated by E&M look completely different than particle collisions that are mediated by QCD. If you look at an electromagnetic process, this is E plus E minus goes to mu plus mu minus at LEP. And here you see an absolutely beautiful 2-to-2 QED reaction. This is proton-proton collisions at the LHC, and you see it produces a massive amount of particles that come out just because of the fragmentation associated with the confining potential of QCD. So we want to measure proton structure, but it's complicated. How do we do that? In essence, we're talking about using a microscope. Microscopes have scales in them. If we think about an ordinary optical microscope, you're using visible light to interact with a surface, and then you observe the light and you learn something about the surface. That's limited by the wavelengths or the energies of the photons you use. So if I'm using visible light, then my energy scale is a couple of eV, and my length scale, my wavelength, is on the order of a few hundred nanometers. If I want to go to something smaller than that, I have to use something with a shorter wavelength. I can't use visible lighting. So the next most powerful thing you could go to would be perhaps a scanning electron microscope. What is a scanning electron microscope? It's a little particle accelerator. You use thermal excitation to generate a beam of electrons. Your electrons scatter in the material, and by measuring the deflection and the interaction of the electrons, you can reverse engineer what the image was. There, you're limited not by the wavelength of visible light, but by the energy of the electrons that you generate. And so you can measure things that are at much, much smaller scales. Once you're already moving from photons to electrons, it's now not a huge jump to say, well, now what happens if I plug this into the LHC or to Hera, and now I have hundreds of GeV worth of energy that I can do this with. In that case, it's exactly the same principle as a scanning electron microscope, except now we're operating at essentially unlimited energy, limited only by what we can put into the accelerator, and then able to probe down to distances that are now far inside the proton itself. At these scales, when I'm delivering so much energy to the proton, you blow it up. And you have to blow it up if you're going to pull a quark out. And so this is what a typical DIS event looks like at Hera, the electron, the proton. You see beautifully the scattered electron, maybe a Brem photon or something, and then you see all of the explosion of hadronic fragments that come on. Sort of the miraculous thing about it is that the only thing you really need to measure to be able to learn something about proton structure is the scattered electron. You can try to look into the details of those fragments for TMD structure and other things like this. But if you just want inclusive hadron structure, the only thing that you need to look at is the scattered electron. So it's very powerful. We've had a long and distinguished line of deep inelastic scattering experiments. The first one, of course, being at SLAC. That was partly responsible for the discovery of QCD itself. That was a fixed target experiment with 20 GeV beam energy. The highest energy DIS experiment ever conducted was Hera. That had a center of mass energy of around 318 GeV. And now we're focusing on the development of the electron-ion collider. The center of mass energy is not projected to be as large as Hera, but it has a great flexibility of what it can collide. Variety of ions, great polarization control, so that between all of these different factors, we expect that we should be able to look deep into the high density regime of QCD, even though we're not getting to as high an energy as you could at Hera. Okay, so that's the background. I want to connect now to what we talked about yesterday in terms of the X dependence of these things. So if I'm looking at the deep inelastic scattering amplitude, in field theory, this is something that has an electron coming in, it interacts by a photon, and the photon does something in the target. If I don't know the structure of my target, I can't say yet in any more detail what the blob looks like. But I do know very well what happens on the electron side. The QED part of the interaction is extremely well understood. So what I can do is I can take my general amplitude squared, or my cross section, and I can split it up into one piece that comes from QED, that I just calculate at tree level, and I'm done. The rest of it contains the QCD information, but except maybe in a toy model case, I don't have the ability to sit down and just compute the hadronic tensor. This is some non-perturbative matrix element that reflects the structure of the proton. So in some sense, what we want to learn about the proton is all contained in that W mu nu tensor. The tensor is not necessarily the best structure to try to describe the structure of the proton because it has those indices floating around. You can instead take the W mu nu, which is a function of two 4 vectors, P mu and Q mu, and do a tensorial decomposition in terms of Lorentz invariant structure functions. And that's typically what's done. So your hadronic tensor depends on 2 momenta, P and Q. But once I do a decomposition in terms of scalar structure functions, then they can't depend on a vector. A scalar function can only depend on scalar quantities. So there are exactly 2 non-trivial scalar quantities that I can construct out of P and Q. One of them is Q squared. That's the virtuality of the incoming photon. For deep inelastic scattering, the incoming photon is space-like, so Q squared is negative definite. So you define capital Q squared as the absolute value of that, which takes into account that minus sign. And if you write the definition of Q squared in lab coordinates, it's some measure of the energy coming in, the energy of the scattered electron, and the scattering angle theta. So the larger the angle theta for a given energy, the larger the Q squared. The other quantity which is invariant and that people use to describe DIS is X. This is specifically Bjorken X. It's a kinematic variable in DIS. The definition is Q squared over 2 P dot Q. If you want to interpret it in the rest frame, it's Q squared over 2M times the energy transfer. Maybe it's useful to say the energy transfer is related to a lifetime. The 1 over the energy is related to a time scale for interacting with the target. So if I want to convert from a dimensionless quantity Bjorken X into something more physical, perhaps, the physical scale is referred to as the Yoffie time. This is the typical time scale in the proton rest frame over which the virtual photon probe interacts. So the analogy that I like to make here is the deep inelastic scattering is a camera, and all cameras contain resolution scales. There's a sort of pixelation or a granularity, which is what Q squared describes. Q squared is essentially a transverse scale because it's space-like. You can go to a frame where the only part of Q is Q perp, and Q perp is Fourier conjugate to a distance, 1 over R. So your typical transverse distance, which is probed in DIS, is of size 1 over Q. So that when Q is much, much larger than a GeV, you're measuring not global properties of the proton, but a local concentration inside the proton itself. In terms of the camera analogy, the Yoffie time, or X, is like a shutter speed. There are some quantum processes that happen inside the proton very, very quickly. And if your camera has too slow a shutter speed, you're not going to be able to see them. But if you boost to higher and higher energies, so I make the energy larger, I make X smaller, and I time dilate the process more and more and more, so that quantum fluctuations that used to be, I don't know, too short a scale for me to resolve, as I go to smaller and smaller X, the relativity boosts those fluctuations, and I become able to resolve not just the long-lived quantum fluctuations that look like the valence or near valence structure, but something deep in the radiation structure of the proton itself. Trying to draw the picture can be kind of strange because you can talk about it either in the rest frame of the proton, the rest frame or the electron. The picture can look different depending on what frame you're in, but it's all consistent. It's all just special relativity. So you could describe it either as a time dilation effect or a length contraction effect, depending on which frame you're in. It's all the same. So this is the physics idea that I want to get across to you about X. X is describing a time scale. And as I go to higher and higher energies, I'm boosting the system more and more. So I'm able to resolve more of the radiation structure inside the proton that lives for a short time, not just the valence permanent properties of the proton that are easy to see. So what is X? There are many types of X, and to some extent they are equivalent, and to some extent they're not. So let me illustrate a connection between two of these types of X's. Bjorken X is a kinematic variable in DIS. You'll also often hear Feynman X. We talked about a version of this X a little bit yesterday as just a fraction of the energy or fraction of the light cone momentum of a particle inside your hadron. Just for illustration purposes, how do these two things relate to each other? Suppose I'm doing tree level DIS, just the handbag diagram. My cross section or my amplitude squared or my structure function is going to look like an on-shell integral over that final state struct quark. So I integrate d3k over 2 pi cubed to e, and then I have my amplitude squared, whatever that is. The point that I want to make here is just about the on-shell condition for that outgoing quark. If I write it like this, I've already used the on-shell condition to write this as d3k over 2e. If I undo the on-shell condition, then I can put d4k and a delta function that selects just the on-shell value. My delta function puts q plus k squared equal to technically m squared. But if I'm working in S going to infinity, I don't worry about the masses. So I have delta of q plus k squared. I only want the positive energy component. And then if I take my kinematics, say in right frame, think of that as sort of a center of mass frame between the proton and the photon. Here my proton is going only along plus. The virtual photon has a negative piece along plus. That's in order to make it space-like. And it's got a large positive momentum along minus. So I can think of the photon as coming along the minus z-axis, the proton coming along the plus z-axis, and my center of mass energy is that p plus q minus product. My parton that I pull out of the proton has some fraction x Feynman of its plus momentum. The minus momentum is small. I don't have to worry about it. Then it has some perp momentum. And then when I compute the particle that actually arrives in the final state, it has whatever the difference in momentum is for its plus component, large minus component, small perp component. And so now if I take the square of this vector, I potentially have something large because I've got a large p plus and a large q minus. But I have a delta function. This needs to be 0. So if I compute this, I have 2 x Feynman minus x Bjorken p plus q minus. And if I pull out my overall factors, which is just 1 over s, this is a delta function that sets Feynman x, the wave function property of what parton you saw inside the proton, equal to the kinematic value you measured, Bjorken x. So I want to emphasize this because these are two very different conceptual things. X Bjorken is a kinematic variable that you don't control. You do an experiment, you say, where did my electron go? And you recalculate, I got this x and this q squared. Feynman x is a property of the proton wave function. We would like to map out the proton wave function as a function of this x variable. How do you do it? You do the deep inelastic scattering experiment many, many times. You collect an ensemble of data at various x and q squared, and each time it's basically taking a snapshot of the proton wave function at this particular value of x Feynman. So this is the statement that there are multiple definitions of x, but they're sort of all connected to each other. This exact delta function is only true at leading order tree level kinematics. If you do next to leading order kinematics with final state radiation or loops, then you smear the kinematics and it's no longer exactly equal, but it's still dominated by something in the neighborhood of x Bjorken. Okay, so that's the definition of x. This was the structure function decomposition that I mentioned. These are the plots actually from the Nobel lecture, Friedman, Kendall, and Taylor, I think. So this is showing sort of the two main results that came out of the early deep inelastic scattering experiments. One was the Callan-Gross relation, that this cross-section is proportional to the point-like Mach cross-section that we discussed yesterday. And then you have, in principle, two structure functions that are in principle allowed to depend on two variables, x and q. And the fascinating observation was, one, the two structure functions are not independent. F1 and F2 are related to each other such that F2 is approximately x times F1. And you see that as q squared gets large, the data sort of saturates where that difference is around zero. This is known as the Callan-Gross relation, and that particular relationship between F1 and F2 is characteristic of a spin 1/2 particle. So the fact that this is satisfied is evidence that quarks are fermions, spin 1/2 fermions. If quarks were scalars, then one would have again a relationship between F1 and F2, but it would be a different relationship. So this is part of how you know that quarks are real. They're not just a classification scheme for organizing hadrons. The other thing was Bjorken scaling, that your structure functions could depend on two variables, but actually they only depend on one. They're essentially a function of x only. They're essentially a function of x only and independent of q squared, unless you change your q squared by a very large margin. That Bjorken scaling property is quite baffling because it seems to imply that what you see inside the proton is point-like structure. You see a point-like spin 1/2 particle inside it, no matter what your resolution is. So if I look just barely inside the proton at q squared, I don't know, 2 GeV squared, I see a point-like quark. And then if I dial up my q squared to 10, I zoom in much further, and I still see a point-like quark. And if I dial it up to 100, I zoom in and I still see a point-like quark. That's the meaning of Bjorken scaling. And that's weird because quantum mechanics is allowed to fluctuate like crazy at short distances. QED and the Heisenberg uncertainty principle allow you to have almost unlimited quantum fluctuations in energy and momentum over very short distances and times. So this is bizarre. Why are the quantum fluctuations not blowing up as I zoom into quantum scales? The only reason that makes sense is if the coupling constant, the probability of those quantum interactions, is also going to zero at short distances. The only way to resolve this was asymptotic freedom. You have to turn off the quantum interactions at short distances, which is the exact opposite of what QED does. So that's sort of the origin of where our picture of the proton comes from. When you look at the parton distributions that you extract from deep inelastic scattering, this is the picture that you see. Often you see them plotted on a linear axis, and the gluons are divided by a factor of 20 to fit them on the same scale. Honestly, that's a terrible decision. The log scale is a much better representation of what the actual structure of the proton is. You see sort of two generic features. There's one set of curves that lives at large x, and there's a different set of curves that live at small x with very different properties. That means that the structure of the proton changes radically depending on where you look at it. If I measure the proton in the large x region, what do I see? I see mostly up quarks, down quarks, peaked around x of about a third, and I've got about twice as many up quarks as down quarks. That's exactly my naive valence picture of the proton, consisting of 2 up quarks and a down quark only. If my proton was exactly this in a non-interacting theory and the 3 quarks were sitting there perfectly at rest inside the proton, each one would share an equal fraction 1/3 of the proton energy. But if you look at the location of the peaks, it's not exactly at 1/3. It's downshifted a little bit because QCD is an interacting theory. And whatever valence quarks you started off with interact with each other and they generate radiation. That radiation bleeds off some of that energy. This is that radiation distribution. It consists of a gluon distribution, which grows very rapidly at small x. And if I have an abundance of gluons, with only 1 extra power of the coupling, the gluons can split into quark-antiquark pairs of pretty much any flavor you want. This is the quark C. And we see that the quark C grows essentially proportional to the gluon distribution. So my point is that there are two very different pictures of the proton. At large x, you see a dilute proton that looks like a 3-body system or close to a 3-body system. At small x, the proton looks completely different. It's filled with radiation, overwhelmingly full of gluons and to a less extent quarks. So what I'm interested in here is what happens to QCD at small x when I go from the dilute region of QCD to the dense region of QCD, where multiple scattering on a huge number of gluons that I radiated all becomes order 1, and my probability to radiate even more gluons is also order 1. So the physics of QCD in this regime, the dense limit, is going to be very different from the physics of QCD in the dilute. So we expect that something radical is going to change about X about deep inelastic scattering when I go to small x. And indeed, we see exactly that. If I look at the PDFs, when I go to small x, I see an explosion of the gluon density. If I look at the structure function F2 as a function of x, as I go to small x, I see an explosion of F2, which is an explosion of total color charge density, electric charge density inside the proton. This was a really fascinating result from the Hera collaboration years after Hera turned off. They've continued to analyze the data that Hera stored. And one fascinating thing that they found was that if you include more and more small x data in your deep inelastic scattering fit, and you pretend that there's nothing happening at small x, everything is DGLAP evolution, large Q squared physics, and there's nothing at small x. If you try to do that, what you get is this green curve, where the more small x data you include, the worse the quality of your fit gets. It's not a massive degradation in the chi-squared of the fit, but it is systematic. The more you include at small x, the worse your description of DIS gets, assuming that there's nothing at small x. And if you take that nothing at small x hypothesis and you add leading log resummation of 1 over x, resumming this multiple emission of gluons we talked about yesterday, then you go from the green to the blue. That leading log resummation of x stabilizes the chi-squared. It seems to be evidence that deep inelastic scattering needs small x behavior, log 1 over x resummation, to adequately describe the DIS data from Hera that we already have. So this is an indication that something fundamental is changing about the interactions and the theory as you go to small x, which is what we expect. So the next part is, how does that change? How does the theory look when I go to small x? If I'm doing deep inelastic scattering at large x, the process looks like this. My proton is sort of in the valence region. I send in my virtual photon and I knock a quark out of it. So I think of this as a knockout process of DIS. The problem is that as I try to go to small x, there aren't any valence quarks anymore for you to knock out. So this process ends up being suppressed as x goes to 0. If I literally just take, say, a tree level diagram in QCD, gamma star, say this. Say I have a quark, gluon. If I compute something like this, what you find explicitly is that this cross-section scales like x to the first power as x goes to 0. And as we discussed yesterday, x is roughly q squared over s plus q squared. So this also goes to 0. So let's say it goes like 1 over s as s goes to infinity. So the process that dominates deep inelastic scattering at large x is not the same as the process that dominates DIS at small x. Instead, since this process becomes power suppressed when I go to small x, the most important contribution is an alpha S correction to it, where instead of hitting something out of the proton, my virtual photon just fluctuates into a quark-antiquark pair, and it punches through the proton, basically like a baby proton-proton collision. In this case, I pay an extra factor of alpha for my splitting, but then my interaction is mediated by gluons, which is all leading power in x, as we showed yesterday. So this process is leading order in alpha, but suppressed with x. This process is leading order in x, but suppressed in alpha. And as x becomes small, that x suppression is far more important than any suppression by alpha. So what you end up with is sort of a process that looks like this. In DIS, you are literally creating a quark-antiquark dipole at the amplitude level that's probing the gluonic properties of your proton as it moves through. Those quarks and antiquarks that are coming in have almost infinitely large center of mass energy. And that means they have a very long wavelength. They see all of these gluons in the target coherently. So when we talked yesterday, we had a single scattering of the, let's say, large P minus quark scattering with background field A plus. This was order 1. And then now if I have many such interactions, all of the same order, dot, 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 what I end up with is basically a line integral. And it's this line integral. So if you say, take this exponential and you expand it to lowest order, you get 1 plus IG A plus. That's the single potential insertion. The line integral exponentiates that. So now you have not just one, but arbitrary number of insertions. This quantity is referred to as a Wilson line. This is the natural degree of freedom that emerges at small x, where I don't just have a single quark, but something which is highly boosted and interacts many times. So sort of instead of thinking about doing perturbation theory here because G is small, I think about G small and A large such that the whole quantity is order 1 and it has to be kept. That's the physics that we're after. This should look quite familiar with what we discussed yesterday. So this was the conclusion that gluon exchange is unsuppressed with S. And if I have many such interactions, they are resummed into a Wilson line. And I know that at small x, I'm going to have an abundance of gluons to scatter on that will produce my A, which is large, due to multiple emission of gluons that are logarithmically enhanced with large S. The statement that I made now is about the cross-section or about the structure function, but because the cross-section is connected to the PDFs through factorization, if my cross-section looks like dipoles, my PDFs look like dipoles. You can make an operator level statement about the PDFs here. The large X PDF is something like this. If I go to small x, then I include the corrections where my psi doesn't just pull something out of the target, it creates a quark-anti-quark pair. That looks something like this. So we talked about sort of the high energy, the coherence, and then things moving along the light cone direction. A nice consequence of that is that the process is very conveniently described by time-ordered perturbation theory. You can really think of it as I have a particle moving along, say, the light cone plus direction, and it sees gluon fields from the minus direction the whole way as you go. So it's very nice to say I have sort of a time-ordered picture. I might have something coming in. It might have some splitting here. Those particles will then also pass through the shock wave. It's very convenient to describe this as a time-ordered wave function. My operator that describes the interaction in the background, and then if there's other wave functions, you include those too. So for deep inelastic scattering at small x, where you fluctuate from a photon into a QQ bar pair, there are essentially two ingredients. One is a set of QED wave functions that describes how my virtual photon splits into a quark-anti-quark pair. That's QED. You can calculate that very precisely. It's exactly the same as if you had photon goes to mu plus, mu minus. All of the interesting QCD stuff is here in these Wilson line operators. Where does this come from? It comes from these 4 diagrams. Think of a virtual photon coming in, and then the virtual photon interacts with the proton here where the cross is. There are 4 possible time orderings. I could have the virtual photon comes in, and the photon is what passes through the target. The blue line here is supposed to represent the gluon field of the target. It has many, many gluons in it, but it's very Lorentz contracted down to a delta function. So we often describe this as being a shock wave of gluons. And that time-ordered picture helps us organize the calculation. If the photon goes through the shock wave first, it doesn't interact. And then if it splits after, there's no interaction at all. So this is an interaction that has wave function squared, and the operator is 1. There's no interaction in this term. Something like this is the opposite. Here I have the virtual photon, it splits, and now I have both my quark and anti-quark running through that shock wave. That produces 2 Wilson lines, one for the quark, one daggered for the anti-quark. So this one produces, let me write it out here. Interestingly, that last diagram cancels because it gives you 1, because you have, for the amplitude level, let's say trace of the 0 V1 dagger from the amplitude. But then in the complex conjugate amplitude, I have exactly the opposite of this. When I complex conjugate this, I have V1, V0 dagger. 1 over MC. So for that last diagram, I have, it looks like 4 Wilson lines, 4 interactions, but they cancel each other pairwise. So my first diagram and my last diagram just give me 1. That's here. The non-trivial part comes from the quantum interferences, where I have nothing on one side, and then I have a single quark-anti-quark dipole amplitude on the other side. So I have, say, 2 1s, and then from my quantum interference terms, I have minus a trace of the Wilson line where the quark is at 0 and the anti-quark is at 1, and the complex conjugate. So this is an operator expression, just sort of rewriting the PDF or rewriting the DIS cross-section in terms of these new degrees of freedom. If the cross-section is built out of dipoles, the PDF is built out of dipoles. And this is the operator reflection. So what we really want to do then is study what are the properties of this dipole operator that controls the whole energy dependence of the process. We already know how it starts. We've done the tree level calculation. We've done the tree level calculation of a single gluon. We've squared it. You've done it for the case of, say, a quark scattering on a quark. It's not much harder to do a quark and an anti-quark scattering on a quark. You just have 4 combinations where the gluons could go here, 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 or here. And when you add them up, you get not just logs, but combinations. So the initial conditions we know very well. The fascinating part is what happens when I include the radiative corrections that we discussed yesterday. If I start off with an operator that looks like a dipole at 1 energy, and now I dial up the energy by an order of magnitude, then I can stimulate the emission of an extra gluon at mid-rapidity. And that gluon that comes out can do a great many things in this overall cross-section. So I have 1 gluon correction to my dipole in all possible ways. I could have a gluon correction which is emitted from one of the quarks and absorbed by the other one. And then that gluon can either cross the shock wave or not cross the shock wave in either order. I also have corrections where the interaction is from one quark to itself. There are corrections that are sort of vacuum-like corrections before or after the splitting. Sorry, before or after the shock wave. And then there's also corrections that go through the shock wave itself, where I radiate the gluon then sees the proton, and then it affects how it recombines. So the exercise is to compute all of these diagrams to leading logarithmic accuracy. I'll sort of break it down where this comes from over the next few slides, but this is the mathematical version of this diagrammatic expression. On the top, I've sort of indicated it as a differential equation, d dy. So if I ask, what do I get for every factor of y, or for every log of 1 over x? And I get a set of alpha s corrections that look like this. This is the same thing written as an integral equation. Instead of a derivative, I have overall dipole equals initial condition plus an integral for quantum evolution. Either way, it's equivalent. So what we want to show out of this is, what is this kernel for this splitting wave function? Where does it come from? And what's the combination of operators that describes overall how the, not just QQ bar, but QQ bar plus glue system scatters on the proton? So let's discuss the features of this. There are a great many elements that all come together. So consider the case, consider the case where the gluon that's emitted passes through the shock wave. When it passes through the shock wave, it changes the operator. So let's say when I had just the quark and the anti-quark, I had trace V dagger. Now in this case, I have a trace of V, and then I have color matrices TA and TB describing the emission of my gluon. And once the gluon's emitted, it also has a Wilson line of its own, scattering in the target. So that operator looks like this. I have my original V0, V1 dagger, now with color matrices TA, TB in between, and now an adjoint representation Wilson line for the gluon. Exactly the same structure, but using adjoint representation generators instead of core fundamental generators. So this is a transformation where a simple operator now becomes a more complicated operator. You start off with sort of a 2-point dipole amplitude. This is evolving into a 3-point dipole plus gluon amplitude. In contrast, if I have a diagram that has the same structure, but it doesn't go through the shock wave, then I don't change the operator. The scattering operator is still just a dipole trace BV dagger. It's also interesting to note that the wave function part in coordinate space is exactly the same for these two diagrams. Really nice property of these Wilson lines is that if I'm coming in at some transverse position x perp, and I come out at some transverse position y perp is equal to x perp. My Wilson line is essentially a delta function of y perp minus x perp. It's a statement that the shock wave is Lorentz contracted to a point. And so even though you're doing a finite momentum kick at that point, it takes 0 time. So in 0 time, your quark doesn't have time to recoil. It comes out here with a momentum going in a different direction, but its transverse position is still the same. So for that reason, all that matters is if my gluon came from quark number 1 and quark position 1 and it ends up at position 2. It doesn't matter whether that gluon goes through the shock wave or doesn't go through the shock wave. It has the same wave function because adding the Wilson line doesn't change the position. So that's one set of combinations. I'm going to have structures like this that have the same wave functions, but different operators that want to subtract from each other. I also have different structures depending on whether I have a gluon emitted only from one parton or something that connects between two. This comes from the form of the wave function. Let me just sketch it in position space. So the wave function in transverse position space looks like x perp vector dot a polarization vector over x perp squared, so that your psi squared goes like 1 over x perp squared. So if I have something like this where it's the same wave function twice, I have 1 and 2 that emitted the wave function, 1 and 2 that reabsorbs the gluon. Then I have this case, a wave function, same wave function complex conjugate. So in this diagram, for instance, I'm going to have a 1 over x21 squared, the distance between x1 and x2 squared. That's the wave function. For this one, I would similarly have 1 over x02 squared, the distance between 0 and 2. That's different from the wave function structure that will occur here, where I have a different wave function for the emission and the absorption. Then I'm going to get a minus sign, and I'm going to get a product, 1 x perp over x squared dot a different x perp over x squared. So I get a cross term of this. And depending on whether those gluons go through the shock wave or don't go through the shock wave, they'll either have the same Wilson line operator or a more complicated Wilson line. So when I put the elements together, it looks, for instance, like I might have actually 2 logarithms for my integral. So if I consider a combination of diagrams like this, I have my coefficients, I have an integral over the rapidity of the emitted gluon, I have an integral over the transverse position of the emitted gluon. And then I have 2 combinations. I have a piece where the operator that's scattering is the dipole, and I have a piece where the operator that's scattering is a dipole plus a gluon. I wrote that operator here. You can simplify the operator using some of the color properties of TA, TB, and the gluon Wilson. Skimming over those details, that lets me rewrite everything in terms of fundamental Wilson lines, where my interaction of the gluon at position number 2 now appears as a V2 and a V2 dagger, rather than a U2, a single gluon Wilson line. So a couple interesting things about this integral. We see the log 1 over x here, or the log of s. This is the log we expect to get. This is potentially something new. This looks like it's also going to become logarithmic, and that it would be logarithmically dominated when x2 is very close to x1. That's almost the case, except for the fact that the operator in brackets goes to 0 in that limit. If x2 is basically on top of x1, then this Wilson line cancels, that dipole goes to 1. And then this becomes V0, V1 dagger, exactly the same as this. And they cancel, you get 0. So it's interesting that the wave functions have potentially a high probability to create fluctuations that are very close to one of the quarks. But there's a cancellation between real and virtual emissions, where you can't tell, basically, at very short distances, whether what you have is a single quark or a quark with a gluon on top of it. That's a property called color transparency. It has to do with asymptotic freedom in QCD, that if you have a very, very small system, its interaction probability is really small. So if I have a gluon on top of my quark, it makes no difference. That's the reason for this real virtual cancellation, that there's, in the limit where these things are on top of each other, the operator becomes the same, and then it's just unitarity. I have certain probability to emit the gluon or not emit. So when I have all of those pieces together, I have a single operator structure. And then I end up combining the wave functions in an interesting way. So we had diagrams where the gluon was emitted from the upper line. We had something like 1 over, let me write it this way, x1 minus x0 perp squared. We had another term that was 1 over x2 minus x0 perp squared. And then the cross term that we found had something that looked like minus 2 x1 minus x0 perp dot x2 minus x0 perp over x1 minus x0 squared, x2 minus x0 squared. This is just a perfect square. This is equal to x1 minus x0 minus x2 minus x0 squared over x1 minus x0 squared, x2 minus x0 squared. These guys cancel, and this is x12 squared over x10 squared, x20 squared. This is the famous BFKL kernel. This is the piece that appears here in the emission kernel for your gluons. So this is the small x evolution equation. Depending on what approximations I make to this, I could call this the BFKL equation, the BK equation, the Bolitsky hierarchy, which is equivalent to the Jim-Walk equation. There are many ways that we have to approach trying to solve this. But this is sort of the starting point for everything. You have a simple operator to begin with, and your quantum evolution tries to transform it into a much more complicated operator. This is really complicated because now if I try to do 2 steps of evolution, my dipole became something more complicated. This more complicated object is going to become something even more complicated at 2 steps of evolution. And at 3 steps of evolution, I'm going to end up with a system that always has more and more complicated scattering systems with more partons in them passing through the shockwave. So I start off with something that looks like this, and then my correction looks like this, and then the correction looks like this, and so on and so forth. And every time I'm increasing the complexity of my operator, which is passing through the shockwave. That means this is not a closed differential equation. You cannot just solve the equation as written. There is actually an infinite number of differential equations that you would all have to solve simultaneously. If I wanted to solve this, I'd have to write down another differential equation that tells me how this operator evolves, and the one after that, and the one after that, and all of them together. That's referred to as Bolitsky's hierarchy of operators. There's an infinite number of operators that you would have to consider. You can't solve it. You can't solve an infinite number of differential equations simultaneously. What you can do is solve it in certain limits. If I try to solve this differential equation in the dilute limit, where my scattering amplitude is small, so my S matrix is small, then I essentially expand the product to linear order. And then I linearize the integrand. Now I just have dipoles and not infinitely more complicated operators appearing on the right-hand side. This equation is closed. It only depends on a dipole, and you can solve it by essentially Laplace-Mellin transform. And the answer that you get is that your dipole amplitude and therefore the DIS cross-section, PDFs, everything that comes from it, it grows like 1 over s to a power, as we anticipated yesterday, and you can calculate that power directly in perturbation. So the exponent is something proportional to alpha s that you can compute. This is referred to as the Pomeroy intercept. That's the solution of the BFKL equation. That describes, let's say, a power law growth of the gluon density with x, or equivalently, an exponential growth as a function of rapidity. So this is the part where your gluon density is blowing up. Yes. So the problem then is this at dilute limits gives you a gluon density that's blowing up exponentially. That full nonlinear equation captures then the transition where the multiple scattering effects from those higher operators change it from being an exponential growth to something that saturates to a finite maximum. The essence of this is sort of gluon recombination. It's the difference between what we calculated yesterday, where I had scattering and a gluon that was emitted, but the gluon that was emitted does not scatter itself. Versus now, if the gluon is in a shock wave, the gluon scatters equally well. It's no longer an independent radiation. It's a radiation that sees all of the density that's already there. So that introduces these recombination terms. The other way that I can solve the equation is in the extreme high density limit, especially with the help of large NC. So I essentially need to justify a mean field approximation to be able to solve this equation in closed form. I have an infinite hierarchy of operators, but if I can take my average brackets and just split them up and say this average of a double dipole is the same thing as an average of the first dipole times an average of the second dipole. That's a mean field approximation. That gives me this. I've factored the product. In doing so, you ignore correlations between. So you have to have a good physical reason why you're able to ignore the correlations. One way to justify that is by taking the large NC limits of QCD. I don't have time to go into the technical details of that here, but there are some comments of it in the appendix from the lecture notes yesterday. Large NC QCD suppresses those correlations, and that satisfies this mean field approximation. Another way that you can justify it is by imagining that you have a very large nucleus with a number a to the 1/3 of protons and neutrons in it, with a to the 1/3 going to infinity. Then for a large system, the correlations are suppressed in powers of the number of particles you have. If you solve this equation, then this includes those multiple scattering nonlinear high density effects, and that's where gluon saturation comes from. What you find is that instead of the gluon density blowing up indefinitely, it slows down tremendously. If you look at the gluon distribution in phase space, instead of being sort of a pure power law, which is what we computed yesterday, these multiple scattering effects change the behavior at low transverse momentum. In particular, it cuts it off at a characteristic momentum scale, and there's a kinematic 0. This picture is sometimes referred to as the color glass condensate, although to be honest, it's a terrible name because it is neither a glass nor a condensate, but it's a little bit like both. It does have color in it. It's kind of like a glass because time dilation has slowed down the dynamics tremendously, although not frozen them. And it's kind of like a condensate because you have a large occupation of gluons in a particular momentum state, but it's not really a Bose-Einstein condensate. The key idea here is that you're generating a high density of gluons from multiple scattering, and that the multiple scattering leads to a dynamical screening effect at low transverse momentum. The basic idea is that if I have a particle that's running through many, many gluons, the color that it sees is random if every gluon you see is an independent gluon. It's literally a random walk in color space, and that leads to screening. You tend to see something that's on average charge 0, or screening towards 0. That's this dynamical effect that the more color sources I have, the more I wash out the behavior at low PT by a bunch of random momentum kicks. Basically, what that does to the gluon distribution is it takes all the gluons that were at really low momentum, kicks them around a little bit, and it spits them back out at a higher momentum than they would have otherwise had. That characteristic momentum scale is called the saturation moment, and that's the natural variable to describe the approach to gluon saturation. Okay, so just to conclude, the essence of this is that the situation that we have right now is unsustainable. What we know now is that we see an explosion of gluons at small x. We see that DIS needs leading log BFKL resummation to correctly describe the data. But it is unacceptable to stop there. It cannot be the case that nature is BFKL and nothing else. Because if that were true, it would violate the fundamental principle of unitarity of quantum field theory. Because without those multiple scattering corrections, my Wilson line, which is this dipole S matrix, it grows without bounds. And so that S matrix should always be less than 1. But with just those linear corrections, essentially your opacity of the medium just gets blacker and blacker. You can always put more and more gluons into it. You can always increase the scattering probability more and more. And unless I include those nonlinear effects, I blow right past 100% probability at a particular point, and my theory is nonsense. Gluon saturation solves this problem. I refer to this as the little unitarity problem. How does gluon saturation solve it? Those nonlinear corrections that we discussed slow down the evolution so that you never reach 100% on the S matrix, or sorry, the T matrix at finite kinematics. Only at infinitely high energy would you saturate to 100% density. And so there's no blowing past the unitarity limit. So gluon saturation solves the little unitarity problem, which is great. Unfortunately, it does not solve the big unitarity problem, because overall unitarity of, say, proton-proton scattering depends not just on a point, but on the entire transverse area of the collision. And what you find is that even though at a point it's well behaved and it stops at 100%, the area, which is at the black disk limit, grows as you go to higher and higher energy. And eventually the growth of that radius of the black disk takes over and threatens to dominate the total cross sections. So for this, you need sort of non-perturbative physics to explain where unitarization comes from. The beauty of saturation is that since I'm talking about it at a local point, I don't need non-perturbative physics to understand why this happens. This happens at short distances where I can understand it's in perturbation theory. Yes, so why should we care about gluon saturation? It's a fascinating state of matter by itself. It is the most intense gluon beam you can ever have. It's like a gluon laser of all coherent gluons with the maximum intensity allowed by nature. It's also interesting because we create such a system in heavy ion collisions when we want to measure a quark gluon plasma. The thing that's really nice about it is that it's analytically calculable in QCD. If I'm working in the limit s going to infinity, a to the 1/3 going to infinity, where I have a very large, very dense system, I can calculate all of this perturbed. So the concluding message that I want to leave you with is, why is this so important? The reason that I went through all of these elementary details yesterday was because I want you to really have in your hand, where does this come from? Why does this happen? The reason that we have an explosion of gluon density at small x is because QCD is a non-abelian theory. The same commutators, the same non-abelian generators that give nice properties like asymptotic freedom that we like, simultaneously give us dangerous properties like an explosion of gluons at small x that we don't like. You can't have this without having that. And this is the demonstration. When we computed that gluon radiation, we saw a perfect cancellation between initial state radiation and final state radiation. And in an abelian theory, you just get zero. But in not just QCD, but any non-abelian theory, you will not get zero. I don't care what the commutator is, as long as the commutator is not zero. And as long as the commutator is not zero, you're going to have this. You're going to have an explosion of gluon density at small x. So my claim is, this is not just a property of QCD. This is a property of non-abelian quantum field theory. And that's huge, because QCD is our only template for what a fundamental theory of nature could ever look like, because QCD is asymptotically free. QED is not a fundamental theory of nature because QED breaks at the electroweak phase transition. QCD doesn't break. It seems to still work up to infinite Q squared, but only if you can understand and solve the infinite S problem at the same time. So I would argue that gluon saturation and its discovery is comparable to the discovery of the Higgs boson, in the sense that the Higgs boson for the standard model was an absolutely necessary but undiscovered element for internal consistency of the theory. And when the LHC was looking for the Higgs and they hadn't found it yet, people were having this interesting discussion about, what if there isn't a Higgs? What if they don't find it? And in some ways, the what if it's not there question is the more interesting scenario. That's what I would return to here. We think gluon saturation will exist, but what if it doesn't? What if we're wrong? If we're wrong about everything. We're wrong about all high energy quantum field theories, and we're wrong about what every fundamental theory of nature could ever look like. This is why this is so fundamental. We have to know if gluon saturation is real or not, because then that tells us whether we're even doing quantum field theory consistently. So I wanted to leave you at the end of these lectures with my bold claim about why gluon saturation is so important, and enough tools that you can judge whether you believe that for yourself. Thank you very much.
Very comprehensive view. Any questions or comments?
Why can't the exchange gluon interact with the shockwave?
The exchange gluon is the shock. So I'm saying we had sort of scattering like this. So suppose I did my quark scattering, and then I would have one gluon exchange like this. Now suppose I have many quarks in my target, and now I have another scattering that takes place on a different one. And I've got another one, and now I've got another scattering that takes place on a different one. So now I have a huge number of these partons in the medium, such that every time I scatter, I have enough that I can scatter on a new one every time. The sum of all of these things together, all of it happens sort of infinitely Lorentz contracted to a delta function, sort of delta of x minus. So all of these things are contracted to a point. So when I say the shock wave, what I mean is any number of T-channel gluons, just like we calculated yesterday. Could be one or two or any number.
Oh, I meant the radiative corrections, the like.
Oh, it does. So yeah, that's really important. So in the dilute limit, sort of by assumption, you're working in a case where the medium is so dilute that the gluon that's coming out does not rescatter. So let me put it this way. So there's always diagrams like this where the radiated gluon just doesn't happen to pass through the shock wave, and then there are diagrams where it does. If I'm evaluating this thing on the right in a dilute limit, I wouldn't keep both the scattering of the quark and the scattering of the gluon. I would expand it to lowest order in a dilute system. So that's how I get BFKL. So that's this one. So when I expand in a dilute limit, I basically either see one scattering or the other scattering, but never both at the same time. That's what the dilute limit gives me. And in that limit, my equation describes exponential growth of gluons as a function of rapidity. But then if I take the same expression, which includes actually those things that you were asking about, the multiple scattering of the gluons, that's the part that has this nonlinear correction to it. When I keep the nonlinear correction to it, for instance, by a mean field approximation, then that changes the behavior. And so those nonlinear corrections are exactly what turns it around and gives you the approach to gluon saturation. So that the rescattering of the emitted gluon is the entire proximity.
Those digits.
Yes, absolutely. So that's another interesting consequence that sort of DIS at large X tends to produce beam remnants and a monojet. DIS at small x tends to produce dijets. So yeah, you can absolutely tag on both dijets. An exclusive process along these lines is one of the candidates to try to measure Wigner distributions, where you can measure, say, the proton stays intact, and you can measure both diquarks, or sorry, both dihadrons or dijets and the scattered proton together. No, only if you want the Wigner functions for that. If you just want, say, inclusive PDS or something, then you can just tag on, say, one of the produced jets. Sure. Well,
Very large, right?
so maybe that's the point that I want to make here, is that there's not really much of a difference between, say, Hera at infinite energies and the LHC at infinite energies. Because even though your probe is an electron, your electron at small x is fluctuating into a tiny proton system. So the systematics of DIS at high energy will look a lot like the systematics of proton-proton scattering at high energies, because it's QCD scattering on QCD by gluon exchange. I guess the main difference is really sort of the kinematics, the frame dependence, that this process looks like a baby proton-proton scattering, but in the photon-proton center of mass, not in the lab frame center of mass. So it's a lot more analogous than it seems at large X. Yes, please.
You mentioned that even if there's saturation, there's still a big problem, like the big unitarity.
The big unitarity problem, yes.
Is there any evidence from non-perturbative techniques that is solved?
Oh, great question. I don't know the answer to that. The papers that I cited, where is it? Here. There was an argument in the small x field about whether this had completely solved the unitarity problem. And there was basically a set of papers that said, look, we've solved the whole unitarity problem. And then these guys came back and computed the radius of the growing black disk and said, no, you didn't. So as far as I know, I'm not aware of any major progress on this since then, but I haven't really checked. It'd be fascinating to look.
Argue that great total cross sections, elastic cross sections of protons.
Yes, absolutely.
Pomeron is exchanged, and therefore they grow. They would violate unitarity at some point, unless they flatten.
Yeah, absolutely. So that's related to, let's say, the difference between the exponent that you get here in perturbation theory versus the exponent that you get if you fit to proton-proton data. You do get 1 over x to the power here, but the power that you get if you fit to proton-proton data is much larger than this. So sometimes people refer to it as the hard Pomeron and the soft Pomeron, or the perturbative Pomeron, versus something non-perturbative that's mediated that energy dependence. But yeah, I guess the important point is that we have something that we can learn perturbatively about unitarization, but we can only learn so much perturbatively about unitarization.
see any, so let's thank.
All right, thank you very much.
Just a few logistical announcements. Again, this evening, we don't